Hello and welcome to this video on deriving constant acceleration formulae. This pulls together work from the Mechanics Year 1 AS and it actually looks at deriving them from a graph and also deriving them using calculus. The first part, which is regarding graphs, is dealt with in the constant acceleration chapter of the textbook that goes with this, and it's the chapter 9 in the Pearson Mechanics one. The second part of this, which looks at the calculus, this actually links to the chapter 11, which is the variable acceleration. However, in both cases, though they come in different chapters, they are all about the constant acceleration formulae. And they're all brought together in just one video. Okay, so let's get started with deriving, and we need to use a velocity time graph. So on our page here we have a velocity time graph. Velocity is on the y-axis and time is along our x-axis. And if you notice, u is the initial velocity and v is the final velocity, and we know that the area under the graph is the displacement, and we know that our gradient of our line is the acceleration. So it's important we remember those aspects of the graph before we get started. So let's look first at using the gradient to help us find an equation relating to constant acceleration. Well, our gradient, as we've just said previously, is the acceleration. And if you remember back to GCSE, when we first looked really at gradients, we did used to draw on a triangle, and we used to look at the change in y, which would be this section here, over our change in x, which is this section here. So the change in y would be v take u, and that would be over the change in x, which in our case is t. Now, rearranging that, I could write that a multiplied by t equals v subtract u, and therefore v equals u add at, which is one of our constant acceleration formulae. So we've actually proved the first one. Brilliant. So let's go on and let's now go about proving the second. So as again we mentioned earlier, our displacement is the area under the graph, and for us the area under the graph is this here. And if we look at that shape is a trapezium, and that's the first thing we need to realise, is that the area under the graph is a trapezium. And we know how to find the area of a trapezium, or I hope you do. If you remember, it's half of A add B multiplied by H. Now, remembering back to those good GCSE days, A and B were your parallel sides, and H was the height. So let's mark on where A and B are on our graph. So A and B are the parallel sides, so that's A there, and this here is B, and H, which if you remember is the height between the parallel sides, would be this here, so that would be H. So remembering that the area under the graph is the displacement, that would equal a half of the parallel sides added together. Well, the height of this parallel side is u, the height of this parallel side is v, and h is actually t. And that there is a formula that we've already used, though sometimes we have written it like that. But either way, it's the same formulae for constant acceleration. So that's both of them now derived from our velocity time graph. So we're now going to move on, and we're going to look at using calculus to derive constant acceleration formulae. So using calculus, here is the question we're asked. Given a body has constant acceleration a, an initial velocity u, and its initial displacement is 0, prove that v equals u plus at, where this is the final velocity. So if we remember back to before, we know that the velocity is equal to the acceleration differentiated with respect to time. Now, if you haven't remembered that, you do need to go and look back at one of my previous videos, which actually covers this in 11.4. So this does require that knowledge. So velocity is equal to acceleration integrated with respect to time. So integrating that, we would have at, or velocity equals at, plus, and we mustn't ever forget, the constant of integration, which is something students do forget, but not you, because you're going to be brilliant. Now, here we need to look back for extra information so that we don't have the constant of integration in our final answer. So if I go back, I'm told that the initial velocity u and its initial displacement is 0. So what does that tell me? Well, it tells me that when t equals 0, then my velocity is equal to u. So substituting that information in, I know that u equals at. Now t is 0, so that's 0, add c. So therefore c equals u. And substituting that back in, I end up with v equals at add, and instead of c here, so if I just point out, I'm using that, and I'm substituting in my newfound value for c into here, I now can write add u. And rearranging that, you'll notice it's v equals u plus at, which I always think is amazing. It actually pulls all of the maths we're doing together. So you've seen it graphically. You can see how that links to also us integrating, which I think is fantastic. It gives you that greater understanding. And B, so I'm now going to have a go at the displacement, and for this I am going to move on to a new page, but I'm also going to have to take with me this v equals u plus at. So moving on to that new page and writing v equals u add at. So again, we've got to think back to that previous lesson, that lesson 11.4, and we know that displacement is equal to the integral of v, velocity, with respect to time. Well, from part A, I found v equals u plus at. So I now can put in here that s equals the integral of u add at with respect to time. So I'm going to integrate u plus at with respect to time. So using my great integration skills, I end up with that. And what mustn't I forget? Add c. And you can already see that this is becoming that formula that we very much want to find. But we need to go back and look if we got any information. They're called initial limits. They can be different things to give you information of what is that value for that constant of acceleration. We can't just ignore it. We can't just drop it off and just forget about it. So going back here, I'm told its initial displacement is 0. So initial means at the beginning when time t equals 0. So I know that when t equals 0, s equals 0. So when t equals 0, s equals 0. So let's put that information in now. S equals, let's erase that, because I know that my displacement, s, is 0. And here, ut, well, t is 0, so that's 0, plus at squared, well, t is 0, so 0 squared is still 0, plus c. So what does that tell me c is? C is equal to 0. So therefore, I now can move on and just say that finally s equals ut plus half at squared. And there we go. I've proved that is my Suvat equation, and again I've used my calculus knowledge to do that, and we're linking all of our maths now together.